Hello, and welcome to our webinar on acoustic floor systems. Today we are going to look at how sound transfer in building works and what regulations are applicable across the UK. We'll finish up by taking a look at our range of flooring systems designed to reduce the impact of noise on building occupants. It is estimated that up to a third of UK households experience noise-related problems, with a third of these directly related to noise from neighbours. As well as an increase in living density and more construction of flatted developments, widespread use of home cinema systems and hi-fi equipment has contributed to driving this rise. Design trend, such as laminate floors or stripped carpets to exposed floorboards, have also added to the problems. Before we consider how to address these problems, let's begin by looking at some of the terminology used and how this relates to buildings. There are two types of sound we are concerned with when designing buildings: airborne sound and impact sound. Airborne sound typically originates from sources like TVs, home cinema and stereo systems. Human voices are also a source of airborne sound, but it's generally bass frequencies from entertainment systems that create the most issues, and these are the most difficult sounds to restrict. This type of sound is caused by the source vibrating the air to create sound waves. When these waves strike the walls, roof or floors of a building, they are converted into vibrations in the structure, which then transfers the sound around the building. This sound is then re-emitted by other surfaces, in the same way as a speaker generates sounds. Airborne sound can come from outside the building as well as within, and typically travels in all directions throughout the structure. Building regulations therefore require most building elements to have some degree of airborne sound resistance built in. Impact sound. Impact sound occurs when mechanical impacts cause vibration in the structure directly rather than via an external sound wave. Impact sound comes primarily from footsteps, and it is here that bare floorboards or laminate flooring cause problems, as carpet and underlay contribute a lot to reducing these impacts. As with airborne sound, these vibrations pass throughout the structure before being re-emitted in other areas. Unlike airborne sound though, the regulations regarding impact sound are typically only concerned with sound transmission between the floors of a building. Acoustic properties. We'll now take a look at some of the properties of walls and floors that can affect the sound transmission within buildings. A thorough understanding of these factors is important when designing structures to perform well acoustically. Mass. When considering acoustics, the mass of a wall or floor is a very important factor. The heavier the element is, the harder it is for incoming sound to induce any vibrations. This has the effect of reflecting a greater proportion of the incident sound waves, resulting in less sound being transferred into the structure. Heavy elements such as brick walls or concrete floor slabs are therefore better able to restrict the passage of sound, particularly those problematic low frequencies, than lighter timber frame structures. It is, however, not always practical or economically viable to use high mass constructions. This is particularly true in refurbishment projects, where increasing the mass is often impossible. Stiffness. The stiffness of the structure is important as it dictates the ability of the structure to vibrate. While the mass of an element restricts the absorption of sound waves, the stiffness restricts their transfer once absorbed. The property governing this is the modulus of the element, in other words, the ratio of depth to length. A shallow and wide beam will vibrate more than a deep and narrow one, allowing for a greater amplitude of vibration and therefore more sound to be transferred. A related property here is resonance. Every part of the structure will have a frequency at which it vibrates more readily. This is the natural or resonant frequency. If the natural frequency of, for example, a wall, coincides with a frequency in the incident sound, the effect may be to amplify rather than reduce the sound. Careful consideration of the stiffness and frequency response is therefore necessary to avoid this. An effective way to prevent sound transmission through structures is by physically isolating one side from the other. This can be achieved either by using entirely separate structural elements, such as independent floor and ceiling joists, or by using resilient mountings for floor and ceiling surfaces. This approach aims to break the pathway for sound to travel through the structure from one side to the other. With independent structures, there is an actual discontinuity in the pathway, leading to the best acoustic performance. However, this approach results in very thick wall or floor elements, so it is not always practical, and as such tends to be used only when acoustic performance is the primary concern, such as in recording studios. Resilient layers are usually a cheaper, thinner and lighter weight solution. They can be applied in the form of floor deck or batten systems, as ceiling mountain bars, or commonly both. These work similarly to car suspension by damping the vibrations and reducing the energy from sound waves by allowing a degree of movement. These systems must be carefully matched to the loadings expected on floors, as heavy weights can damage the layer and reduce their effectiveness. Absorbency. Absorbent acoustic materials work by reducing the echoes within cavities in a wall or floor construction. This has the effect of breaking up the sound waves in these spaces. It reduces the overall energy transfer by converting the energy in the sound waves into heat due to friction between adjacent fibres. Fibrous material, such as mineral or polyester quilts, are usually used for this purpose, most commonly in timber or steel-framed structures. If there are voids present, partially filling them with an absorbent material will generally help reduce the sound transfer. Flanking transmission occurs when sound can pass around the sides of an element, for example, bypassing a floor construction by going through the walls instead. This can result in elements with well-designed and specified acoustic insulation failing to perform as well as intended. Flanking transmission can be minimised by paying attention to how linkages between floors and supporting walls are designed. However, outside of new build constructions, this can be difficult to achieve. It is therefore not uncommon in refurbishment projects to over-specify the acoustic insulation to account for the unknown quantity of flanking transmission. Acoustic floating floor systems will typically use a strip of foam at all perimeters to prevent physical contact between the walked-on surface and the surrounding structure. Building regulations. The building regulation for acoustics have remained relatively stable since the mid-2000s. The precise details vary across the UK, with slightly different variations used in England, Wales, Scotland and Northern Ireland, but there is a lot in common, which we will consider here. The regulations set requirements for impact and/or airborne sound transmission across separating walls between adjacent properties, and for airborne sound only within a single dwelling. Between dwellings, floors are required to resist both impact and airborne sound, and walls to restrict only airborne sound. Between dwellings and commercial properties, such as shops or offices, only airborne sound insulation is required. Where a roof terrace or balcony is over a dwelling, impact sound insulation is required. These requirements are expressed by way of a single figure value, which combines the sound levels across the full spectrum of frequencies into a single number. Depending on the regional variations across the UK, this can be weighted to emphasise different frequencies or make the requirement more or less stringent. In general, though, acoustic requirements are expressed in terms of decibels, dB, of reduction in sound pressure. For airborne sound, this is expressed as dB dNTW, with a higher single figure value indicating better acoustic performance. For impact sound, dB LNTW is used, with a lower number indicating better performance. The requirements are reduced slightly for refurbishment and conversion projects to reflect the practicalities of introducing acoustic insulation into existing structure. This can include period features that are listed, or unknown existing details or defects that cannot be easily remedied. These single figure values do not vary linearly with perceived loudness. A change of 10 decibels in the acoustic performance equates to a doubling or halving of the perceived loudness. This makes the scale used very sensitive, but also makes it very difficult for the human ear to detect subtle variations in acoustic performance. Testing and compliance. Because of the difficulty in accurate perception by the human ear, an important aspect of the regulations is a mechanism to ensure compliance. Again, the specifics of this differ between the various parts of the UK, but pre-completion testing of at least some portion of separating walls and floors feature across the country. Acoustic testing is a complex process and should only be undertaken by those appropriately accredited by organisations such as the United Kingdom Accreditation Service, UCAS, or registered with the Association of Noise Consultants. Testing for airborne sound is typically done by using an omnidirectional speaker to play a predefined pattern of noise, which can be measured by sensitive microphones and sound meters in adjacent rooms. The figure quoted is the difference in sound levels across the partition, so a higher figure the better. The sound source used is usually pink noise, which has equal power per octave, giving more weight to low frequencies than white noise, which more evenly distributes sound power. This shift in frequency is quite noticeable when the two colours of noise are played back to back. Impact sound is measured using a tapping machine to simulate footfall. Tapping machines use a camshaft to drop carefully calibrated weights in a precisely defined rhythm. This sound is then measured in the room on the other side of the separating floor. In the case of impact sound, only the level in the receiving room is measured, so a lower result indicates better performance, the opposite way round from airborne sound measurements. The equipment used to measure this sound must be very sensitive, so during testing it is crucial that certain site conditions are met. The building under test should be more or less complete, with doors and windows in place. A lot of noise can transfer through openings, so it is also important that vents and ducts are also in place, or their openings sealed. Site noise should also be minimised during testing. Ideally, testing should be undertaken at night when no work is being done on site and noise from machinery and traffic will be minimised. Any extra noise from site work will lead to poor results or possibly even test failures, so it is in everyone's best interests to ensure the correct procedure is followed. As an alternative to testing, designers can use approved robust detail constructions to comply with building regulations. These are standardised subfloor types to which pre-approved floor and ceiling treatments can be applied. Because these construction types have been tested thoroughly ahead of time and have consistently exceeded the regulation requirements, they can be used without testing, provided they are followed to the letter. The ProctorGroup have floating floor treatments to suit most robust detail floor types, with a range of systems approved in floating floor treatment, FFT, categories 1, 2, 3 and 5. As well as floor type and acoustic treatments, robust detail also includes standard detail for the junctions and connections between walls and floors in order to minimise flanking transmission. Acoustic Floor Systems Overview. There are two principal types of acoustic flooring systems, and a few other less common ones. Batten systems. Batten systems, such as ProFloor dynamic battens, are most popular in new build timber frame floors, and are the top performing floating system. The extra depth introduced between the battens not only simplifies service runs within the floor, but also provides additional void space in which additional fibre layers can be added to boost sound absorbency. The downside to batten systems is that they tend to be thicker, so it may not be practical to apply to all floors if tying into adjacent floor levels is an issue. The ProctorGroup supply a range of batten systems to cover a variety of different project requirements and floor types. Deck systems. Deck systems are much shallower and can provide a good boost to the impact sound performance of a floor. However, they offer little scope to improve the airborne performance. For that reason, they tend to be more commonly used on concrete floors, where the base floor mass does most of the work dealing with the airborne noise transfer. Deck systems are also a good fit for refurbishment projects, where floor-to-ceiling height may limit the scope for using a batten system. Systems like the ProFloor microdeck at only 17mm thick can improve impact performance noticeably while having minimal impact on floor levels, service and internal trim and skirting. The ProctorGroup's range of overlay deck systems are designed to provide the optimum balance of performance and thickness, while accounting for the practicalities of working within existing properties which may not have ideal access. Other systems. Of the less common systems, the levelling system allows a floor to be raised and levelled while introducing a degree of acoustic performance. This is useful in existing buildings where floors may be substantially off the level, or in new build where pre-stressed slabs may be used, which have an inbuilt camber that must be corrected to give a smooth, level finished floor. The ProctorGroup's ProFloor levelling system used specifically designed resilient bases with packing pieces to accommodate variations in finished floor level from 51 to 203mm, while still delivering good impact sound reduction. That concludes our webinar today. However, you can find full information on our range of acoustic systems and services on the links in the description below this video, or by visiting our website at www.proctorgroup.com.
Good afternoon, everyone. My name is Kira Proctor, and I'm the Managing Director here at the ProctorGroup Limited. First of all, I'd like to thank you all for attending our webinar, and thank you very much to the team that put this together. I'd like to introduce Professor Sean Smith, who is the Director of Sustainable Construction at Edinburgh Napier University, and also a Fellow of the Institute of Acoustics. We know him fairly well. As well as leading the development of the robust detail scheme, the ProctorGroup have worked with him on a number of acoustic research and development projects over the years. Sean, are you there?
Yes, I am. Good afternoon, everybody.
Great. So we've had a few questions over email, Sean, and a number are popping up on the chat now. So thank you again for joining us. I'll just kick off and answer away in your own time. A number of email questions. The first one was, what new areas for acoustics are on the horizon regarding sound insulation standards and building performance?
Well, I think one of the things we're seeing happening not only in the UK and in Europe, but internationally, is the pressure to look at extending the frequency ranges down below 100 hertz. So currently in most building regulations in the UK and in most countries around the world, they will measure from 100 hertz upwards, both for airborne and impact sound. Both France and Sweden have been different, and Sweden is extended down to 50 hertz to lower frequencies, both for airborne and impact. And now Sweden is moving to 20 hertz. There is a new international standard which is coming. It was reshaped last year, and this will now come out, we anticipate later this year, as a technical standard. So rather than being a regulation that everyone must follow, and this international standard will give technical guidance for those clients who wish to extend frequency ranges to include low frequencies and bass notes, for example, and to pick up lower frequency sound transmission from footfall noise. And we expect that to come, as I say, later this year.
Okay, this next question ties in quite nicely with that. Noise complaints can occur at very low frequencies, even when separating walls and floors meet the standards. What, in your view, may be influencing these low frequency factors?
That's a very good question. I think one of the issues we've seen in the last few years has been the improvements on the positive side of air tightness in buildings for achieving thermal insulation, etc. The only issue with that is because sound is a sound pressure level. As a result, we don't have any pressure releases like we used to do. So I'll give you an example. Some years ago, we tested a block of flats built in concrete, extremely good sound insulation levels. And if you can imagine, in England, the maximum performance for impact is 62 decibels. This block of flats was recording 41, and for impact sound, the lower the performance, the better. So that's a huge improvement beyond the regulations. And where the complexity comes in is that if at low frequencies, you don't have that pressure release, then people downstairs in the block of apartments might sense where someone is moving upstairs. So even if the sound insulation meets the requirements, people will sense or feel a pressure change as they know that person's moving around upstairs. And you sense that in your tympanic membrane, or what we call your eardrum. And as a result, what we're now tending to find is some people, particularly with low frequencies, have become more sensitive to this because of air tightness values improving, and there's no pressure release for that sensitivity to be unaffected.
Okay, thanks, Sean. There's a couple more via email, but I'm just going to go on to some that are popping up in the chat box now in case anyone needs to leave. So we have one from Mark Jenkins here. In refurbishment projects, is traditional deafening, such as ash plugging, best left in place, or will switching it for a more modern deafening, such as mineral fibre, give a better result?
I think your best, if you've got the possibility of deafening still being there, you definitely want to use it because you've got the additionality of the mass. You could always top it up with a mineral wool-based or fibre-based insulation just to improve some of the airborne sound or higher mid-frequencies. But if the floor has been designed to take deafening and it is there, it's best preserved being kept there. And just one other thing, Kira, which may be useful to people, anyone doing conversions, as soon as someone hands the keys for that building before any works have been done in it, so if you take an office block and you're converting it to flats, the very first thing you want to do is go and do a pre-completion or a sound insulation test prior to starting any works. And the reason for that is you can then estimate what is the existing sound insulation that's there in that property prior to commencing any refurbishment or conversion works. And we know for many clients we've saved them thousands, if not millions of pounds in some projects through pre-conversion sound testing.
And is that something, Sean, that you find clients or people you come across, do they currently overlook and don't do that prior to refurbishment?
Quite often, yes. And the other thing is, by the time they've thought of it, they've already put enough holes within the existing building fabric as they've been looking at services or looking at what sort of cabling and other things are there. So really, before even any of that work commences, as soon as you get the keys for a property that you're planning to convert, you want to get in and get an ANC or a UCAS tester in to do that sound insulation testing to say, what is the benchmark? Where are we at now?
Okay, that's really interesting. Thank you. Joe McDuff, who is a gentleman who doesn't have access to the property above his address, rents out a property and his tenants have an issue with noise from above. Is there a way to assess the performance similar to a U-value calculation so I can get an idea of what measures I could take?
You could measure just solely in the room downstairs to determine what is the specific sound transmission emanating into that property. You'll only know the level of noise that's in it, obviously not the level above. A good acoustic consultant would be able to determine whether that was something that's fairly standard or not. And then again, the next point is the noise coming through, is it excessive, i.e. might it be antisocial behaviour? In many cases it's not. It could be there's just the existing structure has poor sound insulation. But the first thing I would suggest is to ask a consultant to come in and measure what are the typical noise levels that are being received or emanating from upstairs into the property below, and that will give a starting point.
Okay, just going to jump back to another email question here. I often hear about direct and flanking paths of sound. Could you describe further the types of flanking paths for sound transmission in buildings, please?
Well, I think your video showed very well, and compliments on the video, by the way. I thought it was very explanatory and very helpful. In the video, you showed what happens with the flanking path, and often when I speak at seminars, I try to explain to people that if you can imagine you're standing in a room upstairs in an apartment, there's a room below you, and you're just looking at the one wall, it could be the inner leaf wall of the apartment room upstairs. There are 3 flanking paths at every perimeter wall. So in a standard room with 4 walls, you're talking at least 12 flanking paths. We often talk about direct sound through the floor, and there are 2 components to that, but we won't go into that today. And even if you really boost the sound insulation performance of the floor, the limiting factor, as you explained in your video, is the flanking path. So people need to consider all the perimeter walls and all 12 flanking paths that may take effect.
Okay, and Mark has asked another question, as has Joe actually, but we'll start with Mark because he was first. How accurate and repeatable are acoustic site tests? Is the assumption that only a proportion of similar properties need to be tested valid?
Okay, well, let's first of all talk about the repeatability or stroke reproducibility of a test result. If you are doing a sound insulation test result, the likelihood is there is a repeatability of using it. If you got someone else in, but who's using exactly the same piece of equipment, the likelihood is there might be a 1 dB shift, potentially, as a variation. If you start varying the equipment between different testers on the same floor, that can shift at least to a couple of dB, and in one case we've seen 3 decibels.
Okay.
So there are some variations that can occur. And what was the second part? Apologies.
The second part is the assumption that only a proportion of similar properties need to be tested valid?
I think yes and no. That if you were dealing with a series of repeatable constructions, then yes, 10%, 20% sampling is quite common, providing you're picking up any variations in the junctions. That's what is required in England and Wales, and similarly in Scotland. For any variations in the construction, those should be picked up as separate series of tests. When it becomes conversions, I think the scenario is that it becomes more complex, there's a greater chance of variability, and as a result, we know north of the border in Scotland, they will ask for more testing on conversions in terms of a higher ratio. But however, that's an area of risk that people should consider just to feel on the safe side when they're doing conversions.
Okay, great. And again, this does tie in quite nicely, a question from Joe. Is there a central database or somewhere that people can find testers that they can go to?
There are a series of databases. The Association of Noise Consultants runs a database for those who are registered testers and those companies who register under the Association of Noise Consultants testing regime. Also in that database, and how it works is that when a tester does their test, all of that test data is then passed back through the database and it is recalculated. to check the values which have been undertaken, and then the certificate is issued. There's also a UCAS website that lists all of the companies and organizations who are registered, and wait for it if you're writing it down, who are registered to test under ISO 140 or ISO 717. So you go into that database, that will give you the list of companies and contacts.
Okay, fantastic. And I have one final question which has been sent in via email. So if anyone else has any others, please feel free to ask before we wrap up. Technical compatibility is a more common phrase being used by specifiers. What aspects do you consider fall within this remit?
So what we've seen in the last few years is we have seen a change, obviously, with the energy efficiency improvements. We've seen changes in materials, and so technical compatibility is the technical compliance across the different building standards, where you're dealing with fire, structure, thermal, and acoustic. And some of the insulation materials that people have switched to have very low acoustic absorption. In other words, they're not absorbing much sound. That's then leading to issues that don't have the absorption that they thought they would in some of their inner leaf or external walls, or even some of their room and roof zones. And as a result, then there's coming issues with more sound transmission. We're seeing changes in structure, where people are putting in more components. That's creating bridging. So people should be really careful that when they are looking at new system, or they're undertaking conversions, to constantly cross-check between the different standards the influence and effect that changing something may occur to another standard, to ensure they've got technical compatibility.
Do you know, I think that's a really good point, actually, because you're right. People are looking at different sectors of the building independently. So I think that's something that we'll certainly note as well, to make sure that we're advising a more holistic approach, because it's very easy to consider fire or thermal performance or acoustics independently and not look at how that may have an impact. So I think that was a really, really good point made. Good. Okay, I don't see any other questions coming through, so I would like to thank you, Sean, very much for your time. I think that was extremely useful, and it's fantastic to have someone with your knowledge and also an independent view to answer some of the questions that were asked, so thank you very much.
You're very welcome.
Appreciate it. For our webinar attendees, thank you for taking the time to learn more about acoustics and joining us today. Please feel free to check out our other webinars. They're on our website. If you have any questions, we do have a technical team here who can answer them. And equally, if you have any that you would have liked to have asked Sean and didn't get a chance or forgot, please send them through, and I'm sure we'll be able to email them across to him and get an answer for you. You will receive an email with a link to this webinar. Again, that can be circulated to your wider colleagues or anyone that you like, and there will also be a feedback form. If you have time, please fill it out. It really does help us shape how we do these webinars and learn from them and understand how useful they are. So thank you all again, and enjoy the remainder of your Thursday.